Day 129, retake prep. So, I'm going to go through this and we'll write out pictures and diagrams and math on this paper. But on Schoology, what you need to do is to type in the main idea of each question. And the main ideas I have written down here already ahead of time, so you can write down exactly the right words to get credit. So, here we go. Number one, show a diagram to explain why puddles at night appear darker than the gravel road. So, we have a bumpy gravel road here, and then there's a big pothole, and then it's bumpy gravel road again. And we'll have a car going down the road. Thank goodness gravel roads are not really truly this bumpy. But anyway, we have headlights that are shining down, and then they hit the upward side of the bump, and by equal angles it reflects back to your eyeballs. And so you see photons of yellow, red, blue light coming at you from down there, and your brain says, oh, I see this combination of wavelengths. Therefore, I'm going to call that brown in my imagination. I'm going to paint you a picture of brown spot right there. That's because you have all these photons coming from that part of the road. However, over here, this is a nice smooth surface filled in with water. And so now when you have light coming from your headlights and hitting that smooth water, it's going to reflect forward at equal angles. And it is not going to come back to your eyeballs. Your brain does not get any eyeballs from, your eye is not getting any photons from that part of the world, and so your brain perceives that as the color black. Number one then, what you should write down in Schoology at this moment. Have it open, have your Schoology RP 129, retake prep on day 129, have that open so you can type this in right away. Light reflects forward away from eyes. You have to type that exactly, otherwise you will not get credit for it. Is that better? Yeah. Hot diggly dog diggly. Does anybody need more time to type in number one? Okay. Number two. Draw a ray diagram of a flat mirror to illustrate all these terms. Okay, so we have the flat mirror. The normal is going to be the perpendicular line to the surface. Normal. And then we have a ray of light that's going to hit that mirror. We call that the incident ray. The incoming ray is the incident ray. The IN words come together. And then that bounces off, and we call that the reflected ray. The angle of incidence, that is abbreviated theta sub I or theta sub 1, either way. That is going to be the angle between the incident ray and the normal. The angle of reflection is theta sub R or theta sub 2, and that's going to be the angle between the reflected ray and the normal. That is problem number 2. For that, you should write down this key idea. Angles are measured to the normal. Angles are measured to the normal. Remember, you have to type it into Schoology exactly as it appears on this paper. Does anybody need more time? Number 3, sound travels at 340. You hear your echo off a cliff after 3 seconds. What is the distance to the cliff? So I have here the ground, and here is a cliff. Here's a person making the echo. We want to know the distance to the cliff. That's the delta x from there to there. Now, during that time, sound travels from here to the cliff and back. That whole trip is 3 seconds. We don't want to know the distance of the whole trip. We want to know just distance of half of this trip forward and back, just the forward half. So we got to do some adjustments to our data. During the forward half of the trip, the velocity is 340. We want to know the distance of just half the trip forward. The time for just half the trip forward is going to be 1.5 seconds. Multiply both sides by 1.5. 340 times 1.5 equals 510 meters. So, that was question number 3, and the key idea here is we have to cut time in half. Cut time in half. That's the key idea for that kind of echo problem. Number four. A cliff is 100 meters away. How long will it take to hear your echo? Okay, so here we have the cliff, here we have the person, and it is 1,000 meters away. During that time, the sound is going forward and back. Now, we have the distance for half the trip. The delta x that we're given is only half the trip. So the time that I'm solving for here is just the time to go from the person to the cliff. I can make this into a proportion and then flip the diagonals. I end up with t is equal to 1,000 divided by 340. 1,000 divided by 340, and I get 2.9. But that is only the time to go from the person to the cliff. I need to then double that time, and I get 5.8. That's the forward and back time. 5.8 seconds. So, problem number 4, we need to double the time once we figured that one out. Double the time. Number 5, the law of reflection. Mathematically, it could be written as theta sub I is equal to theta sub r. These two angles up here in our diagram, they are equal. That's mathematically. Or we could write it out for your Schoology, angles are equal. Angles are equal. Number 6. Where is the image located in a flat mirror? So let's say that you are standing in front of this big, tall, flat mirror at a clothing store. You are checking out your new duds. You're looking quite fantastic. You look at the mirror and you think to yourself, who is that dashing person in front of me? Oh my goodness. Well, that person in the mirror appears to our brain to be just as far behind the mirror as we are in front of the mirror. So whatever this x distance is here is, thank you. Whatever that distance x is in front of the mirror, the image is behind the mirror. So the image is going to be a slightly smaller version of you in your perception because it's farther away. Okay, so question number 6. You'd write down these words on Schoology. Equal distance behind the mirror. equal distance behind the mirror. Number 7. In a concave mirror, what do you call the point that all parallel rays reflect to? Okay, so let's draw the principal axis that goes through the middle of the concave mirror, and there are two special spots. One is a center of curvature. If the concave mirror made a full circle, that C would be in the exact middle of the circle. And then we have the special place called an F. That is the place that we're talking about, because a parallel ray, parallel to the axis, is going to get reflected through that F spot. Even if it's down low, it's going to go through the F. And on the other side, parallel rays go through the F. Even if it's really super duper close, it's going to go through the F. So this one F spot is called the focal point. Focal point number 7. Number 7, focal point. Number 8, an ultrasound. This is the thing that images your body. An ultrasound works by speaker emitting millions, in the first blank, millions of pulses of ultrasonic. Ultrasonic. Those are higher frequencies than we can hear with our eardrums. Ultrasonic sounds. And listening for the echoes that occur at each tissue boundary. Those 3 words, please type into those 3 blanks in Schoology. Number 9. Draw an illustration to show 2 ways that a concave mirror can magnify your image. Okay. I'm going to try to do this neat. Here's the concave with a focal point and a center of curvature. One location is between the center of curvature and the focal point. If I have an image or an object right there, to find the image, I'm going to draw a line that's parallel to the axis, and it goes through the focal point. Scribble out the incoming ray. And then I have a second ray that goes from the top through the focal point, and then it gets reflected parallel. And I crisscross out the incoming ray. The 2 reflected rays, where do they crisscross? That is the image location. They crisscross right there. It crisscrosses below the axis, so the image is upside down. And you can see just by observation that that image is bigger than the red object. So if I have an object between the C and the F, I get a magnified image that's upside down and in front of the mirror. Okay, now there's a second way of getting a magnified image. And that is if I put the object between the mirror and the focal point. Let's draw the rays for this. The first ray goes parallel, just like in the past, and it gets reflected through the focal point. The next one goes from the focal point to the mirror, and then parallel. Where do these 2 reflected rays appear to have come from? They appear to have come from that one spot. Didn't actually, but it looks that way. They're angled from that one spot, and so that is the image. That spot is above the axis, and so it's an upright image. And you can see again, just by observation, that the image is bigger than the object. So it's magnified. But this is right side up and behind the mirror. So the moral of the story is, if it's anywhere between the mirror and the C, it's going to be magnified. Number 9, put the object between the mirror and the center of curvature. Put object between mirror and center of curvature. Make sure that you write it with the lousy grammar that I have on the paper here. Do not add extra words to make it sound better. It'll be marked wrong. Put object between mirror and center of curvature. Does anybody need more time to copy that down? I'll take that. Number 10. Draw an illustration to show one way that a concave mirror can reduce your image. Thank you. You can either stay here or you can return to your study hall, whichever way you'd like. Okay, so, well, guess what? If between the mirror and the C it magnifies, what would we write down for number 10? Whatever is not between the C and the mirror, right? Put the object farther away than the center of curvature. Would anybody like me to draw a ray diagram to illustrate that? You know what? Since I'm recording this for posterity, I better do it for who knows who's going to be looking at this in 10, 15 years. So here I have the axis once again, and the center of curvature is here, the focal point is there, and then we have the object here. Okay, first line, parallel to the axis. It gets reflected through the focal point. And then it's a line through the focal point. Gets reflected parallel to the axis. Cross off the incoming rays. Where do the reflected rays crisscross? The reflected rays crisscross right here. So this is your image. Oh, it's teeny tiny. Zoom in. Can I zoom in? Oh, look at that zoom action. Man, I'm in the 21st century. So here's where the reflected rays crisscross. It is below the axis, so the image is upside down. And we can see, obviously, that it's a lot smaller than the object. Okay, number 11. 2 most common uses of convex mirrors, at least in my opinion: shoplifting prevention and car side view mirrors. Whoop, let's get that zoomed. Both of these mirrors are like the outside of a bowl. Since it's a curved surface, you have lots and lots of different normals pointing in different directions, and so you can see things from lots of different perspectives, a wider range of view. Number 12. How do funhouse mirrors make crazy images? Different curves. Some parts of the mirror is curved out, some is curved in. In other words, some are convex and some are concave. Different areas of the mirror. Some places are concave, some places are convex. Some are really curved and some are just a little bit curved. And so you have all this mishmash of magnified and reduced images, right side up and upside down images, and they're all smushed together in one crazy picture. Number 12. Shoplifting mirrors are spherical because they allow for a wider range of view. Wide range of view. Same thing for your car side view mirrors. You don't want a car to be in that blind spot. And so to reduce the blind spot, it does not eliminate it, but it reduces it, is to have a curved mirror. So you can see a wider range of road behind you. Here is... I don't have it. I thought I had it. It's not here. Stretch. Here, let me get one out of it. This is kind of messy. In my mind. Somebody probably came up with this idea thinking, I'm going to make $1 million. Everybody's going to want one of these. They probably thought to themselves, gee, if the car side view mirror is just a little bit convex to help you reduce the blind spot by a little bit, I bet you if I got a really curved mirror, you could see the whole road behind you, and everybody would want one of those to be extra super safe. And so here's a mirror that is very curved. You put this at your rear view mirror, and that way you can see the entire road behind you, left and right. Hello. And the winner of the blue sheet of paper is Julian. So anyway, what's next? Number 14, draw two ray diagrams to show that all images in a convex mirror are reduced behind the mirror and upright no matter what. Okay, so very, very far away. Here is the axis and the convex mirror. Here's the person. And here's the focal point and the center of curvature. First line, from the top of the object, parallel. And then it bounces, reflects away from the focal point. Next, the ray goes towards the focal point, but the mirror gets in the way and stops it. The mirror makes it reflect parallel. Very, very far away. Where do these two reflected rays appear to have come from? It appears to have come from a very small person down there. So when you're very, very far away from a convex mirror, you have a very, very small image. It is behind the mirror. It is right side up. If we get really, really close to one of these, I hope that you all get the opportunity to go down to Chicago and see the Bean. The Bean is a very large convex mirror. Oh, I didn't do that very well at all. Here, let's do this again. Okay, now those two curves are about the same. Let's get rid of this so it doesn't confuse you. Okay, the focal length about the same distance away. That's the F, and there's the C. Now we're going to be very, very close. How many people have been to the Bean? It's a sculpture in Chicago. It's a giant. Like a kidney bean, only it's all mirrored. So to one degree or another, it's a convex mirror all around, except for the underneath it where it's like a tunnel. There, it's concave. Okay, to draw your image here, we do the first line the exact same. Parallel, bouncing away from the focal point. Parallel, bouncing away from the focal point. That geometry is exactly the same. It's just that the horizontal part is not as long. The angled part is the exact same slope. It's going from the exact same focal point. The second ray is a little bit different. The second ray is going to be steeper going down, and it's going to hit the mirror higher up. But it's still going to get reflected parallel. So the geometry of this second line is a little bit different. We scribble out the incoming rays. Where do the two reflected rays appear to come from? They appear to have come from that spot right there. So that's where the image is. The image looks a little bit smaller than the person. Not a lot smaller, but still smaller. It's still upright, still behind the mirror. No matter how close you get, you're always going to have the image behind and upright. Here, no matter how far away you are, it's still going to be upright and behind the mirror.